In this lecture, we want to begin our discussion of linked lists. Linked lists are of critical importance to computer scientists. Although linked lists aren't normally used as containers per se, they're very often used to create other more complex data structures. An example of this would be the hash table, which we will study later in the semester. Hash tables provide big O of 1 access time for search, delete, insert operations. They are the high-performance data structure of choice for many applications, and the big O of 1 time makes them extremely attractive. So these are heavily used, and they are built using linked lists. Another important data structure are tree structures, binary search trees, AVL trees, red-black trees, and these structures are also built using link-based structures. So it's important that we understand first how linked lists work so that we can extend this to the more complex data structures later on in the semester. Linked lists are an alternative to arrays. Linked lists can shrink and grow as needed. The problem with arrays is they're never the right size. Or perhaps I should say they very seldom are the right size. It's the case that you might know exactly how many elements you need. But the reality is what most programmers do is they try to guess the largest number of elements they might have to store in the array and then maybe increase that just a bit. So arrays almost always waste memory. However, linked lists are always exactly the right size. When you insert a new element into the linked list, you dynamically allocate memory for that. When you remove elements from the linked list, then that memory is freed up and returned so that it can be reused. With arrays, of course, the entire block of memory is reserved, and whether it's used or unused is not relevant. It's still off limits for any other purpose. So a good example of how linked lists work could be explained by a little story. And this story is about Johnny's birthday. So it's Johnny's birthday, and his father hands him a card. And Johnny's disappointed because he was hoping for cool presents, but instead he has a card. Well, he opens the card and looks, and there are no money in there, no gift cards, just a note. And it says, "Go look in the garage." So Johnny runs to the garage and looks, and there's a brand new bicycle in the garage. Great, that's just what Johnny wanted. But he notices that taped to the handlebars is another note. So he looks at the note, and it says, "Go look under your bed." So Johnny runs up to his bedroom, looks under his bed, and there he sees a video console that he's been wanting. And taped to that video console is another note, and it says something like, "Go look on top of the dryer." And so he rushes to the dryer, and there's another present and a note taped to it. Linked lists work in this way. That is, we have elements, data, the presents as it were, that we're going to insert into our list, but along with the data we also have a note that says where the next thing is. So linked lists contain, each linked list node or item has two pieces, the data itself and also a reference to where the next element is, how to find it. So here we see the beginnings of a public class linked list, and I have an inner class node. This inner class has two fields. Type T, which is the generic parameterized type data, and then a node that will point to the next element in the list. So we have the two fields and then a constructor that initializes those two fields. We have next equals null here in the constructor, and this is done explicitly, though it's not absolutely necessary. In the Java language, references are always initialized to null if not explicitly assigned. Also, I want to point out to you that class node uses a different parameterized type. That's because it's a different class. If we were to put type E in class node, then it would not necessarily conflict with the linked list class, but rather what it would be is a shadow parameter. That is a parameter with the same name that exists in a narrower scope. So there would actually then be two E's inside this class linked list. That is not necessarily desirable, though it's not really a problem. You could use E in class node if you wanted to. Your programming editor may give you warnings. Actually, it's not terribly important because this is not exposed to the application programmer or anyone that would be using the linked list class. They cannot get access to the node class that's inside the linked list class, and therefore this node class is protected. But the right way to do it is to use the T, or at least a different parameter from the linked list class. Again, you can stick with E's all the way through if you want. That's not really a problem. So we have this node class, this inner class highlighted in bold here, and it's a very small, tight class without extra fluff. There is only one constructor. Why would you make a node if you have no data to store? So it only makes sense to have a constructor that takes an argument. An argumentless constructor really makes no sense here. Also, we have no need for get and set methods. The accessor methods are actually slower than using simply the dot operator. So we can refer to the elements inside this list by using the dot operator, and that's a much cleaner and in fact faster way of doing it. So this is a very, very simple class that is just more or less a wrapper for two things: the data we're going to store in the list and a reference to the location of the next element in the list. So then, to add elements to our list, I have here the prototype for an add first method. That is, this method adds to the beginning of the list, inserts it in first position. Anytime you're inserting data into a linked list, the first thing you must do is create a new node. So we have node new node equals new node, and we pass in the object parameter. Now that a node is created, it must be inserted into the list. Access to the list is granted by the head and tail pointers. That's the only way into the list, by using either the head or the tail pointer. So first we check to see if the head is null. If the head is null, that means the list is empty. If the list is empty, then we need to set the head and tail pointers to point to this new node. Otherwise, the list is not empty. Then the next link needs to be set to the head, and then head set to the new node. Finally, we increment the current size, and that hooks up this new node into the list. So I want to switch over to the sketchpad for a minute and look at how all of this works, hoping that we can get to a little bit deeper understanding of what's going on here. So we have a head pointer, and I'll leave some space down here. We have a tail pointer. Both of these are initialized to null because the list is empty to start with. That's the initial condition for the list. Now we make a new node with node new node equals new node. The new keyword causes memory to be allocated for this new node on the heap. And there are two fields inside this node. The data here. And then we have a next link. And this is initialized to null. Now this node has an address on the heap where it lives. To make things simple, I'm just going to use letters to indicate an address. We don't know exactly what that address is, and it doesn't really matter. So I'm going to call this address D. So when we started the method, we created the new node, and then we have the test. If head equals null, Then head equal tail equals new node. The list is empty, so both the head and the tail pointers need to point to or reference this new node. So we are assigning these this way. So now our list is in a correct and consistent state. We have one element. It is both the first and the last element in the list. And the head and tail pointer then both point to it. So I want to insert another element. So I'm going to make a new node, and this one I'm going to call C. It has a piece of data. It's allocated on the heap, and the address of where this node lives is called C. It's initialized. The next field is initialized to null. So having created our node, now we have the if test. If head equals null, it doesn't, it equals D. Therefore, we go into the else block. And that code says new node, the C, dot next gets head. New node dot next gets head. And then head gets new node. C. So now we have two elements in the list. If we start at head, we go first to C, and from C we go to D. And then we hit null. That's the end of the list. So I'm going to add another node, a B. Now we have the test. If head equals null, well, it doesn't, so we enter the else block. New node, the B, new node dot next gets head. New node dot next gets head. Well, the contents at head are C. Head gets new node. Head gets B. Let's add one final node here. We will call it A. Again, we say node, new node equals new node. When we do this, it allocates on the heap space for a new node, returns the address of where that node is, and that address we're calling A. Then in the method, we check to see if head's null, and it's not. We enter the else block, and the code is new node, the A, dot next gets head. Head gets new node. Now remember, these letters are addresses. We've done this as a simplification. And so we have head contains the value A. It's a 4-byte address which we are using A to represent. So we can dereference the head to get to this first node A. We can then follow the chain to go to B, to C, to D. Then we hit null, and that's the end of the list. A very important idea here that I want to call your attention to is that there's a difference between a node and a reference to a node. That is, as we look at this little diagram here on the sketch pad, how many A's are there? Well, let's see. There's an A here, there's an A here. How many B's are there? A B here, a B here. How many C's? Again, C and C. And how many D's? D, D, and D. Well, how is it possible we can have 2 A's, 2 B's, 2 C's? Is this a problem? Not really. What we have is a difference here between a reference to a node versus a node. So, I want to write down some expressions here, and let's see what this means. node current equals head. Sorry, this is an E. All right. So if I say current, what does that mean? Well, what I've actually done is allocated, and on the stack, not the heap. These are class level variables, so they are allocated on the heap. On the stack, in the method, on the stack we have allocated a space here for current, and it has the address A. All right, let's try something. Current equals current dot next. What's current now? Current dot next. What does this mean? What does this refer to? In fact, these chains can get quite long. We'll come back to this in a minute. But suppose I write the following. Head dot next dot next dot data. What precisely does this refer to? What does this mean? The important thing to remember here is how this works. Your very last entity after the last dot operator, this is a field in a node. What precedes it here is which node. All right, so this is which node, and this is a field in this node. So we have head dot next dot next dot data. That's it. It refers to this piece of data. All right, let's try another one. Head dot next dot next dot next. To what does this refer? Remember, this is the node. This is the field in that node. So this is head dot next dot next dot next. The nexts here, this one, are used to identify the node. Head dot next, head dot next dot next dot next. This is a field. It is not a reference used to figure out which node. This is the actual field. So it's important to understand this distinction. All right, so let's go back to our previous question. Current gets current dot next. What does this do? It changes this reference from A to B. Current is the node, A. Next is the field in that node, which is right here. All right, another important point. On the left-hand side, if you have head or tail or a dot operator with a reference to the list, you change it. Suppose I now say current equals null. Does that change the list? No, it does not. It cannot change the list. What that simply does is change this variable to null, but it does nothing to the list. However, back this out, we'll leave this pointing to B. Suppose I do this. current dot next equals null. What does that do? This is the node. This is the field in that node. Go to the node B. The field in that node here, the C, becomes null. Notice that I have changed my linked list. What I've actually done is severed the C and D. They are no longer in the list. Moreover, we're not in a consistent state because the tail pointer still points to D. So this is almost certainly an error that you do not want to make. The point here is it's essential that you understand when we start dereferencing node references exactly what we are doing. Therefore, it's important to understand the difference between a pointer to a node and a node. Current is a pointer to a node. Head is a pointer to a node. Tail is a pointer to a node. But these guys, which are dereferenced using head, tail, or current, are actual nodes. And so it takes a dereference to change them. Now we can modify the list by changing head or tail. If I say head equals head.next, then that changes the list. That would change head to B, and it would sever or remove this A node from the list. So if I have head, tail, or another reference to a node with a dot operator, on the left-hand side, that changes the list. However, if I have temporary variables that I've created for doing things like traversing the list, removing things, assigning or changing those variables has no effect. Given this current list, if we say current equals current dot next, what is now in current? Current has B. This C is current dot next, and the dot next is the field which is right here. This is the node. This is the field in the node. So a question now. I am going to use the head pointer, and I want to get a reference to this piece of data, the data at D, but I want to use only the head pointer to do it. So how would I accomplish this? What would be the statement I want to write? eTemp is equal to, now, what do I want to write? Okay, what's the node? Head dot next, head dot next dot next, head dot next dot next dot next dot data. This is A, this is B, C, D, and finally this last one is the field in the node. So, advantages and disadvantages to linked lists when compared to arrays. First, linked lists take twice as much memory. Not only do you need to store the data, but you need to store a reference or a pointer to the next node in the list. Then linked lists have slower complexity for some operations. If you need to search an ordered array for some element, you can use binary search, which gives you big O of log n behavior. But you can't use binary search with the linked list. Therefore, any operation that involves searching the list is going to be big O of n. You must start at the head and traverse the list one element at a time until you find what you're looking for, or run off the end. Additionally, operations that have the same complexity as arrays have slower empirical times. When we talk about empirical times, what we mean is observed time or wall clock time. Accessing sequential memory is faster. However, using the links to hop around to different areas on the heap is slower. Typically, the CPU has caches, and once you start accessing an array, most of that array will be stored in the cache, and therefore access can be very, very fast, and it's noticeably faster than following a sequence of nodes across the heap. Linked lists are always the right size. That is, you insert or remove data as needed. However, arrays are almost never the right size. Typically, what programmers will do is reserve the largest amount of memory they think they might ever need. And of course, if you run out of memory, you try to insert beyond the end of an array, then the program crashes. However, linked lists can grow up to the amount of available memory. Finally, linked lists are not generally used as containers. More commonly, they're used to build other data structures, such as stacks, queues, and hash tables. It's fairly simple to use composition to build a stack and a queue with a linked list. And this makes a great deal of sense because stacks and queues have big O of 1 behavior for push, pop, enqueue, dequeue, and therefore you're not constrained by the slowness of accessing linked lists as they would be if used as a container. So this concludes our introduction to linked lists, and in the lectures that follow we will be looking at how to build stacks, queues, and other structures using linked lists. We would also be looking at some of the varieties of linked lists, including ordered lists, doubly linked lists, and skip lists, as well as self-organized lists.